Take a close look at the empty space surrounding a magnet. To the human eye, there is nothing there, but this void is actually occupied by an invisible, highly structured force that exerts a constant influence on the world around it. We see this structure by observing how matter reacts. When scattered near a magnetic source, iron filings don't settle randomly, they align with the field. These filings act as microscopic markers, clustering to reveal a distinct geometry, hidden pathways connecting one pole to another. Physicists call this visual map magnetic field lines. It is a standardized language used to translate an invisible influence into a concrete geometric diagram. These rules turn a static pattern into a functional map. By identifying the orientation of these lines, we can determine the specific magnetic environment of any point in space, from the scale of an atom to the reach of a galaxy. To read this map correctly, we build it from scratch using 4 geometric rules. We'll start with the most basic source, a simple bar magnet. Rule 1: magnetic field lines form continuous, closed loops. Unlike electric lines that terminate at a negative charge, magnetic lines have no beginning or end. Inside the magnet, the field continues from south back to north, completing the unbroken loop. Historically, we tracked loops by testing the field at specific points. A compass needle always aligns itself with the local direction of the magnetic field. This leads to Rule 2. The exact direction of the magnetic field at any point is found by drawing a tangent to the field line. This vector, labeled B, gives us the precise heading of the field at that coordinate. While closed loops show the general flow of magnetism, the tangents give us the exact orientation of the field at every point along those curves. Beyond identifying direction, these lines also tell us how much force is present in a region. Rule 3 links line spacing to field magnitude. Lines are sparse in region 1, but tightly packed in region 2 near the pole. Counting lines crossing a unit area gives a relative measure of strength. More lines in that square means a stronger magnetic field. This concentration raises a question. In these high-strength areas where lines are forced extremely close together, do they ever cross each other? Rule 4. Magnetic field lines never intersect. No matter how crowded, they remain distinct paths. If 2 lines crossed, a compass at the intersection would point in 2 different directions at once. Since field direction must be unique, the lines can never touch. Together, these 4 rules transform the diagram from a simple illustration into a mathematically rigorous map of invisible space. To understand how this map works in the real world, we must look at how a moving charged particle actually behaves in this environment. People often mistake these for lines of force. Unlike electric field lines, which push particles directly along their path, magnetic lines only show orientation. The actual force on a moving charge acts exactly 90 degrees away from the magnetic field line. This distinction is vital for understanding everything from the current-carrying coils in a motor to the way the Earth's magnetic field deflects solar radiation. Mastering this visual language allows us to recognize the structured influence that governs everything from the orientation of a handheld compass to the massive magnetic cycles that coordinate the movements of the universe.